Thank you so much, everyone, for joining today. The Epic SEM facility is really excited to announce our brand new Hitachi SU8700 SEM and some of the new or upcoming remote data analysis capabilities that we're going to be offering. And so we have a big group of people here today, Nick, Kristen, myself, and Roberto, to talk about all of these things. And we won't go into too much detail on all things because we do have several other tech talks on some of these topics, but the main goal for today is to introduce you to this new microscope and what it can do. So this new microscope is a consignment, so we have it for about 9 months, and we're hoping that we can get some good research done on it, and you all love it and want it to hang around a little bit longer. So after this after this tech talk, when you do know a little bit more about it, look out for signups for a workshop that we'll be hosting in September on the 17th and the 18th. And that workshop will include application specialists from both Oxford Instruments and Hitachi High Technology. And they'll be sitting with you on the microscope, showing you all the new capabilities. Whatever you want to do with your sample, you can work on it with them. And we'll also host office hours. So if you have questions on how to post-process EBSD data and Aztec Crystal, for example, you can sit down with the application specialist from Oxford and work through that. So the outline for today's talk, we are going to briefly cover some of the specifications. These are just kind of the standard specifications that you see on the website. So it's nothing too fancy. After that, Kristen and Nick are going to go through in more detail the imaging modes on this instrument and all the analytical modes, so all of the Oxford detectors. And then Roberto will come in and talk a little bit about some of the upcoming remote data access and analysis options that we're working on for all of you. I know that there's a lot of different software packages that you guys use, and it's no fun coming to Nuance to sit down at one of the post-processing PCs and do it here. So hopefully you can do it from home moving forward. So the Hitachi SU8700 is similar to the Joule 7900 and Quanta 650 in that it has a Schottky emitter. So a Schottky emitter provides a very stable and high current or bright electron source for high resolution imaging and analysis. It has a very large range of accelerating voltages that you can use. So it's very flexible. You can use low kV to get surface information or higher accelerating voltages for things like backscatter imaging or analysis. These are some of the specifications at different accelerating voltages, really the resolution that you can achieve. And so one of the benefits of this particular microscope is that you can achieve really high resolution at very low accelerating voltages. And so that's something that we're going to talk about at our workshop in September. So if you're interested in something like that, please come by and work with Muto-san from Hitachi on that. Large range of magnifications. So, and large field of view, and also very high current. So if you're doing things like EDS or EBSD, you'll get a lot of signal because you can get really high current in this instrument. One of the very unique things that we're very excited about is the pixel resolution that you can achieve in your imaging. So you can do ultra high pixel resolution for capturing very detailed or large area images without compromising quality. And Nick is going to expand on that a little bit in the imaging modes. And then, of course, you can get a very large field of view. This may not be as large of a field of view as you would see on the Quanta or the Hitachi S3400, but still large enough that you can do large area imaging. And I'll turn it over to Nick to talk a little bit more about the imaging.
Right. Thank you for the introduction, Tirza. And I have seen some of those 40,000 pixel images, and they are just amazing. Such high quality. It's really incredible. So actually, let's take a quick look at one of these, an example. So this is a backscatter image of a rat brain slice that was taken at the 40,960 pixel resolution. And the image on the right is that yellow highlighted region that's essentially just been digitally enlarged. So these aren't two separate images. The 40,000 pixel image just contains that much information in them. So you could essentially blow this picture up and put it on a billboard and you'd still be able to see all the details pretty well. And the field of view for the image is 120 microns on the left, like Tirza mentioned, so it covers a ton of area. Anyways, we're going to move on to talk about some of the imaging modes that the 8700 can offer. And it's got a lot of them, so let's take a quick look here. As you can see, we have 2 in-column detectors, the upper and middle detectors, and 3 in-chamber detectors, the lower detector, the ultra-variable pressure detector for low vacuum work, and the BSE detector. And these 3 aren't the only in-chamber detectors we have, as Kristen will tell you in a bit. We also have several Oxford detectors that we'll need to cram in there, so this thing's really going to be fully loaded. You will need to be careful with all these detectors because some of them do occupy the same space in the chamber, so making sure you back one out before you put the other one in is going to be important. But really, it's a good problem to have here. Now, the upper and lower detectors are going to be similar to others you may have used in the past. The upper detector will give you a nice high-resolution image, low noise, and the lower detector will give you a more topographic view of the sample surface. Both are really useful and they have a ton of applications. And backscatter detector is also going to be similar to other BSE detectors, but it does have that large field of view like in the rat brain image, and it has very high resolution. So it's a 5-segment semiconductor type BSE detector where each segment can be set to either positive, negative, or off. So that right there has a ton of different imaging modes you can set it to, but we'll just consider that as one imaging mode for now, and we'll talk about the other newer stuff here first. So first we'll take a quick look at the middle detector. The middle detector is a really great tool to have on the 8700. It offers in-column BSE imaging, which is really useful on a high-resolution microscope because it allows you to work at very short working distances. So typically, BSE detectors that sit underneath the objective lens usually require a working distance of a minimum of 8 to 10 millimeters or so to optimize that backscatter signal. But you can see from the top right image, we're able to sit at around 5 millimeters working distance for our backscatter analysis, which is really going to help our resolution, and we're still getting good backscatter contrast there. It combines the best qualities of an upper, lower, and backscatter detector into one that gives a great compositional and topographical high-res image. And on top of all that, the 8700 lets you overlay all 3 signals into one mixed signal image, which you can see in the bottom right, to just get all that info into one shot. And each signal is adjustable, so you can play around with it to really optimize your data. So that was a good introduction to the middle detector. Let's move on now to the ultra variable pressure, or the UVD. The UVD is an in-chamber low vacuum detector that lets you do both low vacuum topographical analysis as well as cathodoluminescence imaging. Variable pressure mode lets you analyze non-conductive samples like polymers, semiconductors, and even resins, like this sample here, which is a carbon fiber reinforced resin. The UVD lets you image at very high resolutions without having to worry too much about charge buildup or contamination spots. You can also keep your samples pristine if they're unable to be coated and still get high quality images. This is also a great feature to have on this microscope because it means you can perform low vacuum EBSD to aid in the analysis of difficult or charging samples, which Tirza will discuss more in a following section. And you might be familiar with low vacuum mode, but for those of you who aren't, that's when electrons essentially that escape the surface of your sample interact with and positively ionize the extra gas molecules that are inside that chamber. And those ions are then attracted back to the surface of the sample where they neutralize some of that negative charge buildup. And the ionization events between those electrons and the gas molecules will also generate photons in the form of visible light. This light will help to better reflect the true topography of the sample, so you get good shadowing and good surface detail on the images. Alternatively, the bias on the front of the UVD can also be turned off, which will stop attracting all of the electron ion cascade and light signals from this cascade, and instead starts exclusively collecting the light from the cathodoluminescence, which comes directly from the sample. So you can essentially turn the UVD into a CL detector. And this can help you look at the crystallinity of your sample, find defects and impurities, as well as help you study materials' optical properties, among other things. In this image, you can see that the areas of crystalline dislocation in this gallium nitride substrate. And now there's no spectrometer attached to this, so we'll only be able to do CL imaging, not CL spectroscopy with this detector. But here's another example of the different data you can collect using the UVD as a CL detector. So A is an SE image of a rutile anatase mixture with which are both TiO2 polymorphs, so you can't really see a difference there. B is going to be a backscatter image of the same area, and you can maybe convince yourself that there's some areas that look brighter, but not really, right? It's all the same material. But if you take a look at C, that's the CL image using the UVD. You can clearly see the anatase particles lighting up because they have a higher CL luminescence than rutile. And by overlaying them on the BSE image in D, you're able to tell where your particles of interest are pretty easily. So we just got a good look at the middle detector and the UVD detector, but there's actually one more detector that's kind of hidden. And that's going to be the low KV STEM detector. Everyone always forgets about the STEM detector, but it's actually a really great tool to have alongside all these other ones. The detector sits underneath the sample stage in the chamber, so it can collect transmitted electrons like a TEM, and provides both surface and structural information about your sample. STEM and SEM offers some advantages, such as increased contrast and less sample damage, which is particularly important for biological materials and polymers. You can achieve great resolution using the STEM, though not as high as a dedicated STEM instrument or a TEM, but it's still extremely useful for analyzing things like nanoparticles. So here we have some gold silicon oxide core shell structure nanoparticles, and the STEM lets you observe the layered structure easily. So the denser gold center appears darker in the image than the outer silicon oxide shell. This is, of course, bright field mode, so we can also look at dark field mode. Bright field mode detects unscattered transmitted electrons, so you end up with a brighter signal in the thinner areas or lower Z parts of the sample, like on these carbon nanotubes in the top right image. And dark field is just the inverted form of bright field. So the detector instead picks up scattered electrons and shows diffraction contrast, or which highlights areas such as defects or different crystal orientations, which you can see in the lower left image. And if you look at the mixed image in the lower right, you can overlay both of these signals simultaneously along with the secondary electron image or any other image mode that we talked about, really. Possibilities are basically endless. That brings us to the end of the Hitachi detectors and imaging modes. So now Kristen is going to introduce you to the Oxford detectors on the 8700.
Okay, thank you, Nick. So yeah, this microscope is going to be kind of a powerhouse for a lot of things, including analytical sample characterization. So Nick covered a lot of the great imaging modes. But yeah, we're going to have a few detectors from Oxford Instruments that will help us get a more detailed view about the actual chemistry and mineralogy of our samples. Kind of the line between imaging and an analysis, is, not super strict, but I think you'll see that these detectors are really unique and going to be able to tell you a lot about your samples. So a lot of our users are probably familiar with EDS already, or energy dispersive X-ray spectroscopy, which is when you use X-rays released by electron specimen interactions, which can tell us the elemental composition of our sample. So we're going to have three pretty exciting EDS detectors on this microscope, and each of them will bring, hopefully, your EDS analyses to sort of the next level. We're also going to have an electron backscatter diffraction detector for EBSD, which Tirza will talk about in the next section. So first, let's look just at the EDS detectors, how they differ, and why you might want to think about using one versus the others. I'm not going to go into too much depth about EDS detectors, but if you want to learn more, we do have an earlier tech talk about EDS detectors and how they work, so you can scan this QR code to watch that YouTube video. So first, I want to talk about the Ultimax large area detector. You can think of this as kind of your general purpose EDS detector for this microscope, especially if you're doing your sort of typical high KV EDS or more quantitative analysis. This detector is from Oxford's Ultimax line of detectors, which uses kind of high-end technology to give superior speed and sensitivity without compromising on accuracy. So on top of that, this particular detector from this line is their biggest at 170 millimeters squared. Why does a large area matter? If you're unfamiliar with the concept of a solid angle, you can kind of think of this like the proportion of the area of a sphere that an area takes up. A larger solid angle basically means you're able to capture a larger percentage of the x-rays that are coming off your sample, and more counts is always better. You get better statistics and accuracy. It's faster. It means you'll also get better data in situations that before you might have had very low count rates. Things like if you're using a low kV or accelerating voltage or low beam current, maybe if you're trying to increase your spatial resolution or prevent sample damage. More counts also means it's easier to detect low concentration elements and also light elements if they're needed. This detector is rated with a detection range down to beryllium. So just to give a comparison with the other EDS detectors we already have at Nuance, we do have two other Ultimax detectors on the Quanta and the 7900, but as you can see, this one is a lot bigger. It's more than twice as big as our second largest EDS detector. To give you a sense of scale, the difference between the 10 millimeter detector, like on our Hitachi 3400, and this 170 millimeter detector is very close to basically the difference in the cross-sectional areas of Earth and Uranus. So a very big difference. So next, we're going to have an Ultim Extreme detector from Oxford Instruments. This detector is going to be your go-to detector if you're interested in the light elements and rated down to even lithium. It's also going to be your go-to detector for very low kV EDS, as low as around 1 kV, and you can use this detector up to about 7 kV. Just to give a comparison with an Ultim Extreme detector, which is also very sensitive, you can see that in the low kV range, this Ultim Extreme detector is even more sensitive for those light elements. You can really see the difference here where the red is showing a spectrum from the Ultim Max instead, and then in yellow you have the Ultim Extreme. So really good for low kV and light elements. So why is this detector so good for that? The most notable feature about this detector is that it's windowless. If you're not sure what that means, EDS detectors often have a protective barrier or film on them that helps protect the detector crystal from contamination and also helps to maintain the vacuum inside. The problem is these windows can absorb low energy X-rays before they hit the detector. All our other detectors, EDS detectors at Nuance, have windows, so this EDS detector will be unique here for that. Um, yeah, there you go. So while this detector technically has a bit of a smaller area than our Ultimax, it's also, it actually has a larger solid angle because it's configured in a way that it can be much closer to your sample. So if you go back to this solid angle diagram, you can see that by just decreasing the distance to your sample, the area you need to collect the same amount of X-rays can be smaller. And like we covered with the previous Ultimax detector, this larger solid angle means a lot of things. You'll get better accuracy, it's faster, improves signal for low kV and low beam current, et cetera, that we covered before. And then because also it's windowless, it's going to be better for all those things and really great, even down to lithium. The extreme detector is also designed with a special electron trap and a snout that allows you not to just be closer to your sample, but also allows it to be much closer to the objective lens of the microscope. If you remember from your general SEM training, being close to the objective lens or being at a short working distance is better for high resolution imaging to get a smaller spot size, and also so you can use an upper or through the lens detector system, which are higher resolution. Often with EDS, we sacrifice image quality by choosing parameters better for those EDS count rates, things like working at 15 kV or above, using higher beam currents, and the longer working distances so that the X-rays will go into the detector. And all of these decrease your spatial resolution and can also sometimes increase sample damage and charging. So this is another great thing with the Extreme is you can pretty much just choose your parameters for that optimal high resolution imaging and analysis, and you don't have to change things for your EDS analysis. The electron trap that is part of this detector, while it's really great for allowing this low kV and light element analysis, it does make things less accurate if you're working at accelerating voltages above 7 kV. So you'll still want to use the Ultimax if you're doing higher kV work. So last up on our EDS detector tour is the Unity Bex detector from Oxford, and this is the world's first backscattered electron and X-ray detector. This is going to be your go-to if you're really interested in compositional mapping, and this will do both EDS and BSE mapping. This detector is actually placed directly underneath the objective lens, so it simultaneously can collect BSE electrons and X-rays with a large solid angle for those high count rates. Because it's directly underneath the pole piece, the field of view is much wider. You can even do fisheye images. The working distance is also flexible. You don't have to, work at just that specific working distance to make sure the X-rays get into the detector. There's also no shadowing typical of EDS because it's not placed on an angle. It is directly above. Because of its location under the pole piece, the X-ray detector can get exposed to a lot of BSE electrons, so it has sort of special filters for that. And an unfortunate consequence of this is it's really best suited if you're interested in elements more massive than sodium. If you're interested in elements like oxygen or carbon, which I don't know why you would have reasons to care about those, kidding. You may need to compare the performance with the other detectors to see if they might be more appropriate for what you're trying to figure out. Um, so a big thing with this detector is it's not just that it's great for mapping, it's fast. You can actually map your sample at basically normal imaging speeds. So you can get basically full color images with compositional information in real time. So this is going to make it a lot easier to find rare phases of interest because you can basically just move and scan around your sample and search. Just look for that sort of color difference and find your region of interest. Something like the mapping speed is on an order of 100 times faster. So you can also make large area maps much faster. So what might have been an overnight map before, maybe will take you a couple of hours now. This detector is mainly for mapping, so quantitative EDS and more detailed compositional analysis. You'll still need to probably use the Ultimax or Extreme, but luckily this detector can work simultaneously with the Ultimax, so you can toggle between the two detectors, but not the Extreme. This detector also works in low vacuum mode if you want to do mapping of non-conductive samples. And just to give you kind of an idea of what this might look like in real life and in real time, this is a video showing a battery cathode sample just scanning around, and you can see this amazing quality and the compositional variation as you're just imaging and moving around. You can also then choose to slow down the speed for a higher quality map if needed. Let's let that finish. You get it. Okay. So yeah, just to recap the 3 EDS detectors, we're going to get this Ultimax large area detector for your general qualitative, quantitative analysis. It could also be used in conjunction with your BECS. There's also this Ultimate Extreme, which is going to be great for your light element analyses and low KV analyses, and then the Unity BECS, which is great for mapping and finding regions of interest. So next we'll move on to the eBSD detector. So I'll pass it on to Tirza.
Thank you, Kristen. That was wonderful. Very comprehensive. All right. So the fourth and final Oxford detector that will be installed on this instrument is the Symmetry S3 EBSD detector. So if you do EBSD at Nuance currently, you use the Quanta 650 with the S2. So this is the newer model of the EBSD detector. And just kind of in general, in terms of specifications, it has improved sensitivity. So it's better at detecting weaker signals. And this is really helpful for things like beam sensitive materials. It has a higher pixel resolution, so you can do high angular resolution EBSD or HR EBSD, and it's really fast. So you can see here the number of patterns per second when you're using a specific pixel resolution for your diffraction pattern. And since this technique is, some of the other Oxford detectors are brand new to Nuance, this technique is not super brand new to nuance. This is just a newer detector. There are a few things I want to highlight. So if you want to know more about EBSD in general, I'm going to go over the basics, but we did do a whole workshop on EBSD with Oxford. So if you use the QR code on the screen right now, it will link you to the YouTube video and you can watch that and learn more about what EBSD actually is. And one of the main things I want to highlight in terms of EBSD with this microscope is the transmission Kikuchi diffraction capabilities. The combination of this instrument, all of the specs that we've gone over so far, and this detector will make it very, very useful for transmission Kikuchi diffraction, which many of you may not have heard of before. Again, in this workshop we did, there is a whole talk by an applications or I think he was the product specialist for EBSD on TKD. So please check that out. So if you're not familiar with EBSD or electron backscatter diffraction, it is used similar to EDS and where you can get a spatial information on the composition of your sample, but EBSD, you get spatial information on the crystallography of your sample. So this is a steel sample. If you're just looking at the iron EDS map, you don't see the grains, but when you do EBSD, you can see the grains, you can see some of the twins. And this information is very useful to characterize things like grain boundary characteristics, grain size. You can look at textures or crystallographic preferred orientations or deformation, so strain in the sample or in the crystal. And so just like other mapping techniques, the beam is rastered across the surface of the sample, and this specific geometry where the sample is tilted towards the EBSD detector surface. The beam interacts with the sample and it diffracts off the surface onto this phosphor screen and projects this Kikuchi pattern. The Kikuchi pattern is analyzed and the information on the crystal structure, phase, and orientation of the grains within the sample is recorded. This red cross right here is just indicating where on the screen the beam is placed and the resulting diffraction pattern from that, and you can see the change in the orientation. And so this is really useful in material science, large range of different applications and materials. How it actually works is it collects this diffraction pattern or this Kikuchi pattern for each beam position, and it's transferred to the EBSD software where it's transformed into a Huff transform. And the Huff transform is used to detect the positions in the Kikuchi bands within the pattern so that they can be compared to or those peaks, they correspond to the bands and they can be detected and the angles between them can be measured and then compared to an internals database, which matches the pattern or finds the best possible solutions and calculates the orientation. And so many of you, if you do EBSD, probably do traditional EBSD where you use a bulk material, and there are limitations when doing EBSD with bulk materials. Of course, polishing, you need to have a pristine surface, but you can also see in this cross section right here, and this is your 70-degree tilt sample. And we talk about in our SEM trainings, your interaction volume when the beam interacts with the sample, it scatters and you get this large region or large surface where signal is being emitted. And so because of that, your spatial resolution is pretty low or relatively low in traditional EBSD, whereas if you do things like TEM, use a very thin sample, you can see that interaction is very small. And so you increase your spatial resolution. So you can do high resolution EBSD by doing transmission Kikuchi diffraction. So in transmission Kikuchi diffraction, the beam passes through a thin sample and the diffracted electrons are projected onto the phosphor screen. And so in this geometry, you can see it's not right on axis. It has to diffract into the detector still, but it's in this geometry, it's still very powerful, very useful. This is a paper from, it's actually 2020, I put 2022, but Sugar et al. In 2020, where they compared off-axis TKD, on-axis TKD, and nanobeam diffraction in the TEM. And what you can see is that they're actually pretty similar. You can get similar results in the SEM using TKD. On-axis geometries are a little bit better. You get a little bit more detail. In the nanobeam diffraction, you get more precise angular resolution, but the process of doing all of this in the TEM is a lot slower and it's more complex. So if you don't need that kind of resolution and you want to just do it all in the SEM, doing transmission Kikuchi diffraction could be very useful. One of the exciting things that is coming up that we don't technically have on this instrument, but we hope to have in the future. Oxford just introduced at the Microscopy and Microanalysis Conference their new near access TKD screen. This screen gets inserted on the head of the EBSD detector on the Symmetry 3, which we will have on this microscope. And so you can see it's not on axis, but it's near axis. And this overall for transmission Kikuchi diffraction can increase the sensitivity by decreasing distortions in the pattern. It will be faster, very fast, so you can do high throughput analysis. And just overall improves your spatial resolution. So in this electropolished steel sample here, you can see at a 5 nanometer step size, you can see fine features, but with the near axis, you get better or faster indexing, better quality patterns, and you can start to see at a 2 nanometer step size, even smaller features. So we hope to have this capability available in the future. So please reach out to me if you're interested in this so we can start discussing how to get it here. And with that, I will turn it over to Roberto to talk about some of the exciting things we're working on for remote data analysis.
All right, thank you, Tirza. So now that we learned about all these great capabilities that are going to include with this new SEM, right? So that actually like creates more problems, especially specifically on like how to analyze all this like great data that you're gonna be able to collect. Like, so especially we've been getting like feedback from many users in terms of like how we're gonna analyze all this data, how we're gonna actually like transfer the data, etc. So we've been working here at Nuance on like finding solutions for that. So specifically on this for SEM, right? If you go think about like how what the data they're going to collect now. So that of course they're going to increase the data volume, right? And a complexity with this like multimodal type of acquisition, right? So you can collect EBSD, EDS on top of the images, right? TKD, etc. So that creates more complexity, and then that also increases the challenges in terms of like how we're going to analyze this. And then while like Oxford has been working on like adding those capabilities on the current softwares they're gonna make available for all of us. We still have to sit in front of the computer outside here, outside of the microscopes, and deal with that, right? So for like hours sometimes. So we are working on a solution for that, and then we already on a beta testing phase of that. So the idea is that to show that we need virtual machines and then create this like robust pipelines for data analysis, right? So that will add, help us to, with scalability, right? So to scale that analysis, and we'll be able also to like control the environment that we'll be working on, right? So right now, so we have to pretty much like wait for the next users to finalize the data analysis, and then you go in front of the computer and then work on that version of the software that is available for you, right? So be able, having that on the virtual machine to be able to control like the environments and make the necessary updates to the softwares that will include all the capabilities for analysis now. Also, if you think something more complex, for example, you can create your own workflow for automation, meaning, for example, you collect the data, send the data over to the cloud, and then immediately or almost immediately access the data to analysis, even while you collect a data set, right? So that's something that can help you to have a quick feedback on your data collection, and you can tune your parameters based on the feedback that you have from the data analysis, right? Another a big thing for us here and then for users in general is that how to share the data and collaborate with other users within your group and outside of your group at Northwestern, right? So with that, we also have the capability of like sharing, quick sharing the data to your collaborators and have them like remotely connect to that and help you to analyze and give you like feedback on that. And of course, like from the facility perspective, like for us, it's also like cost efficient, meaning that you have like one license that are available to all of us at the same time, all of the users at the same time, right? And then it will also help us on the training and the development of new tools, and also adding like new workflows, for example, or even like if you're working on like ML models, so you can deploy on top of that and work on a specific data sets that you want to. So for that, what we have done so far, and then is something that is like I said, like is available as a testing for us. We build up on Microsoft Azure. They have their own pipelines and virtual machines that you can deploy, and they're very flexible, right? So if you're familiar with like any of those systems, like AWS, for example, does similar things, you can change your buckets, or like the size of your virtual machine, or and configurations of a virtual machine depending on your problem, right? So we are able to do that, and then we'll be make available to all the users hopefully this fall, and that will help us to first of all like secure the remote access, right? So you have right now, as you know, so you go. There's a couple of steps to get the data on your computer, right? So we are trying to make that much faster for you all, and then also more secure, right? So then you only have access to your data, and other people cannot see your data too. And also that will be done through this Globus application that we've been working on. And also we'll be able to access high performance computing, right, without having the actual like local hardware. So I hope this will help you to really like speed up your analysis, and then be able to analyze the data, all of this great data that you're going to be able to collect at the same time, right? That's our hope here. With that, I guess I'm gonna pass back to Teresa, right? Oh, that's the end. Okay. That's the end.